Okay, continuing with our work on centripetal force, we're going to talk about motion in a vertical circle. So, imagine that what I'm doing is I'm spinning an object around, and rather than spinning it around my head this time, I'm spinning it in a vertical circle of a radius r, and there's some little mass there that's being spun around, and remember this is vertically. So there's the little mass, and it's being spun round anti-clockwise. Now, if we want to work out the force that's required to hold that mass in a circular path, we use the central force equation F equals mv squared over r, or F equals m omega squared r. But if we're in a vertical circle, there's another force that is going to affect what the tension is in the string. And that force is the weight of the mass. The weight of that mass is going to affect the tension in the string at various points around the circular motion. And there are two very special points that we want to think about. In fact, these are really the only two points you're ever asked about. There is the point at the very bottom of the circle and the point at the top of the circle. So at point A, at the bottom of the circle, you need an extra force to support the weight of the mass. Weight always acts downwards, and therefore the tension at the bottom will be greater, because as well as requiring a central force, your tension has to provide a central force, but it will also have to supply a force that balances the weight of the object. At point B, which is at the top of the circle, then you still require a tension to keep it moving in the middle, but the weight at the top of the circle is acting into the middle, so the weight provides some of that central force, so your tension is the central force minus the weight. So you only need a smaller tension at the top. In fact, if the weight is greater than the required central force, then your tension is zero and the mass will fall into the circle. Maybe you want to pause that and think about that again. If the weight is greater than the required central force, then you've got too much inwards force, if you like, and the mass will fall into the circle. So there's a minimum speed really that you need to keep an object moving at, to keep it in a vertical circle. If it's going too slow, the circle will collapse, because your central force has to be at least as big as the weight of the mass. So that minimum speed that you require is when the central force equals mg, and mg equals mv squared over r. We can cancel out the m's and rearrange it, and we get v squared equals gr. Therefore, v is the square root of gr. Now that equation is not on your relationship sheet, but it is a very useful relationship that you should be familiar with. You should be able to show where that comes from. Minimum speed is the square root of gr. Here's another example of the same sort of thing. This is a car going over a humpbacked bridge. If this car is going too fast, it will leave the road. It will fly off the surface of the bridge, if you like. So therefore there is a maximum velocity that this car can travel at and still stay on the road. It's exactly the same type of question. The humpback bridge has got a kind of circular path. It's got a radius of 6 metres. And therefore, we can use the same principle to solve this. Remember, the weight of the car is providing the force that keeps the car moving in that circular path. So it's the weight of the car that provides the central force. So mg equals mv squared over r. Again, cancel the m's, rearrange, we get v squared equals gr. So v equals the square root of gr. Same little equation. Remember, that equation isn't on your relationship sheet, but it is a useful equation for you to remember. Now this time it's the maximum speed though, because if that car goes any faster than that maximum speed, it will leave the surface of the road. And here's the amazing thing with these questions. Mass doesn't matter, because the mass cancels out. The weight of the car cancels out with the central force. So, in that equation, v equals root gr, there is no mention of the mass. It's just 9.8 times 6, 7.7 metres per second, regardless of whether it's a big heavy car or a wee light car. Another example is the roller coaster loop-the-loop. If you've ever been on a roller coaster and it's gone upside down, then that roller coaster car has to be travelling at a minimum speed to stay on the track. If you're not going fast enough, then as that little cart reaches the top, then it could fall into the circle. You don't want it falling into the circle. So therefore it has to have a minimum velocity so that it keeps moving around the circular path. Now, the only force at play here is the weight of the car. So if we want to work out what's the minimum speed required to keep this car on the track, again, we have to balance the weight with the central force. It's the weight that's providing at the very top of the loop. It is the weight that is acting towards the centre of the circle. And we need a central force that is equal to the weight at that point. If the weight is bigger than the central force, the car will fall into the circle. So again, we use v squared equals gr, so v equals the square root of gr. And that will give us the minimum speed. If the car is to go faster than that, then it will stay on the track. But if it was to go slower than this, then the central force would be less than the weight and it would fall, the cart would fall into the middle. So 10.8 metres per second. Again, it might be worthwhile pausing that and having another look at that. And again, rounding to the correct number of sig figs is 11 metres per second. And the last example is a conical pendulum. I don't know if you've ever seen a conical pendulum, but it's basically an object that's moving in a circular path, suspended from a string from the ceiling. We used to have a flying pig in the department that was a conical pendulum. Pig moves around in a circle, is attached to the roof by a string, and there's a tension in the string, and that string makes an angle, theta, with the vertical. And then our object, whatever it is, a little spider or a pig or something, it moves with a certain tangential speed in a circular path with radius r. Now, if we know what that radius is, and we know what the length of that string is, then we can really do a wee bit of vectors here to work out a number of things in this example. So the tension in the string has got two components. It's got a component that's supporting the weight of the object and a component that's keeping the mass moving in a circle. So we have mg vertically, mv squared over r towards the centre of the circle. a component that supports the weight of the object, and a component that provides the central force. Let's do a wee bit of maths. So let's draw this triangle again. Okay, there it is. Remember, the horizontal side of that triangle is the component of the tension that's providing the centripetal force. The vertical component of the triangle of the tension is supporting the weight of the mass. So that hypotenuse is the tension in the string, and we've got this angle theta. Now, tan theta equals the opposite over the adjacent. The opposite side of this triangle is the component providing the central force, so mv squared over r. The adjacent side is the reaction force to the weight, that's mg. Now, it's always tricky doing a kind of double division here. I like spreading it out. It's mv squared over r times 1 over mg. M's cancel and we're left with v squared over gr. Now that's equal to tan theta. So tan theta equals v squared over gr, then v squared equals gr tan theta. And therefore v will be equal to the square root of gr tan theta. And again, that relationship is not on your relationship sheet. I don't think you would ever be asked to show it, but it has certainly come up in past papers where you've been asked to carry out calculations based on the components of a tension in a conical pendulum. Here is an example just to show you what that's like. Same setup, we've got a mass moving in a circle that's got a radius of 0.8 metres. It's supported with a piece of string that's got a length of 1.1 metre, an angle theta, and we are asked to calculate, firstly, what is that angle? What's that angle theta? And then secondly, what's the tangential speed of the mass? And there will only be one single tangential speed that mass can have if it's moving in a circle where that angle from the vertical is theta. So the tangential speed v can only have one value if theta has got a specific value. Right, here we go. How do we find angle theta? Again, we can use some simple trigonometry. Sine theta is the opposite over the hypotenuse. The opposite side of the triangle is r, the radius, and the hypotenuse is l, the length. 0.8 over 1.1. If we work out theta, it's 47 degrees. So now we know theta, we can use the equation we derived on the last sheet there, that v equals square root of gr tan theta. We know what g is, we know what r is, and we've just worked out what theta is. So the only velocity that you can have at that radius and at that angle is a velocity of 8.3 meters per second. Again, mass doesn't matter. You might need to think about that for a wee minute.